So, hello, good afternoon, everyone. I'm happy to welcome you on another TWF meetup, in where we have a pleasure to welcome Jarek, who will be our presenter and speaker for today. Hello, Jarek. I'm happy to see you again.
Hello.
And I think some of the viewers may already know what you will be speaking today about and a little bit about yourself from our promo video, which was posted last week. So maybe I will not hold you back and I will give the stage for you and I will let you bust or maybe confirm some myths about performance testing.
Thank you. Let me share the screen. And yeah, I agree to everything. Let's find the right. Yeah, it's here. Okay. I think you need to add me to. Oh, yeah. Great. Perfect. Okay. Let me. So, ready to start? I guess we are. Cool. So, good afternoon. My name is Jarek. And yeah, today you'll spend an hour with me complaining, bashing, and talking about performance tests. And I hope I will do some myth busting with performance test and talk about first things, how to read the results of the performance test, because it's not so obvious, as you will see in a couple of slides, and then we'll focus on designing performance tests and building environments and what things you need to consider. And at the end, we'll also do have some discussion around tooling and how different tools can be misleading us and showing different values and not always telling us all the truth. Okay, so let's go. Yeah, my name is Jarek, and I live in Kraków, Poland. And for last 5.5 years, I work and still working, of course, at Neo4j, a company that delivers a graph database written in I would say JVM, because we have a mixture of JVM languages. And I'm working as a team lead for the benchmarking team for all of this time. I'm with JVM for the last 20 something years. It's like too long to remember. And mostly focusing for last, I would say, 10 years on low-level stuff in JVM, concurrency, profiling, performance stuff. And yeah, I'm a speaker at conferences. I'm still coding, and I still love it. And I was architect for a short period of time, but yeah, that's the different life. So let's go. So the thing I learned moving myself into like performance world is that I don't think I think many of us don't care about performance, especially these days, where you have, Kubernetes, cloud providers, and things scale with like push of the button. The thing is that in recent year, I see a change in the approach, because the thing that people start to see is like the costs of the cloud. And there's some small shift starting into, okay, we should write performant code because we want to save some money on the cloud costs. So yeah, things I hope will change in the future. The truth is that the ones who work with performance tests, sometimes they do it not as full-time job, but from time to time. And yeah, so they are like even if people work and do performance testing, they are not aware of like understatements and false promises in a world of performance tests. So this presentation will try to like uncover some of these false promises and help you navigate this world. So yeah, welcome to my world. Last 6 years. Uh, and I love this quote, everybody lies. And this is especially true in the world in performance testing. So this presentation should be called performance test anti-patterns, but I think the name I chose is a little bit better. So yeah, let's go. You will see funny pictures because my presentations are usually black and white, and people complain that oh, there are not funny pictures. So I decided to put random funny pictures from time to time. So let's focus on the first performance anti-pattern. Is I call it numbers game. So basically, when you ask random person about performance, they will say, "Oh, the performance is about numbers." Yeah. So operations per second or seconds per operation, so latency or throughput, and we base our decision and our perception also of performance is yeah, it's numbers. At the end, you get a single number and it tells you the truth, which is one big lie. And the problem with this thing is because you think performance is about operations per second or seconds per operations, you use these numbers to make some important decisions in your project. So, for example, you choose technology based on the performance numbers. Yeah, you choose framework X, or you choose language, or you choose cloud provider or database because somebody promised you certain throughput or certain latency. So you make a choice based on this. Based on these numbers, you make some code optimization techniques decisions. So you run performance tests or you run micro benchmarks, and you say, okay, this is faster, so it means it's better. So I will do these optimizations. I will because it works. Yeah. And the thing that is really important for me is, you make decisions about your infrastructure and especially infrastructure resources uh, based on these numbers. So you expect a certain performance, and you say, okay, I will need 2 machines or 4 machines, or the size of instance, database instance, or so on. The truth is that these numbers are one big lie. And the thing that with the performance, there are so many factors that can impact the performance of your code and performance your system under test. But the final number can be really just representation of the state when you were testing the system under specific configuration, settings, versions of software, and so on. And you will never replicate the setup in production. Yeah. So the question is there a value in performance testing if it's not about numbers? If it's not about numbers, what is the deliverable of performance tests? So I love this quote from the X platform uh, from some pretty old book, 91. So yeah, by today's standards, it's pretty old. When the guy was writing about benchmarking wars. So basically, I probably heard this term. Is the situation when some company publishes the numbers and says, "Okay, my product behaves like this." So the other companies try to like say, "Okay, we are even faster," and my company was a part of this game like 2 years ago, probably when we published some benchmark and we had like big response from other competitors that they are actually faster than us. Uh, and this can go on and on because what's interesting is like special case of benchmarking wars, something called benchmarking. So this is the situation where you publish your benchmark for one specific use case that proves that you are faster. So you know that your database is fast on writing or is super fast with some kind of queries. So you only publish the benchmark for this specific use case of your product. And I always joke with my team that actually, if you give me any product, I can prove it that it's faster than any other product. But just by designing the proper benchmark and just by selecting the proper data set. And so that's why I think there's a problem, because you can prove anything with benchmarks, any use case, but you are faster. So the problem is that the numbers are really misleading and dangerous. The other factor of this is the statistics. So majority of time, if you look at benchmarks, like somebody produces public benchmarks or somebody from your team does load testing, people are talking about averages. And yeah, this is really nice article about it. But actually average, at least with the normal distribution, is pretty bad measurement. And I think this chart shows something. If you assume normal distribution, your average will say, okay, 50% of the customers get the expected throughput or expected latency, but the other 50% of customer get worse time response time. So average will say basically says that 50 of your customers will be satisfied with performance, and the 50 will not. So that's the problem with using average, and there's like a lot of articles around in internet that why average is a wrong number to share performance test results. There is also another interesting problem with average is the thing that we expect that for the same input, we will get always the same response time. But with the complexity of the systems, this is never a true. And there is something called random variable, which basically says, okay, even if you have the same input, you cannot expect the same response time over and over again. So if you start to look at performance numbers, I think what is really important is to do some, at least refresh your memory on statistic classes. You don't have to go full steam, but understanding distribution, coefficient of variance, standard deviation, and other things, and average, median, and percentiles will help you to interpret results of your performance test. And here are like pretty good articles which are like, I would say, good enough introduction if you want to start work with performance tests. What is the solution to this anti-pattern? One thing is always use percentiles and always say, okay, for 99% of the request, we had X millisecond per request. Another thing is don't share a single number, don't share percentile or don't share average, but show the histogram and use histograms like in this picture to show you the performance profile of your system under test. So yeah. And now, quite interesting thing is I love this quote. This is from the tool we are using internally in a team. It's called Java Microbenchmark Harness. And when you run the Microbenchmark Harness suite, it always outputs the throughput or latency, and then this small notice message at the end. And I love it. The numbers are just data. To gain reasonable insight, you need to follow the numbers and use profilers. So this is where I think people don't put enough focus is actually you run them tests Of course, numbers are interesting. We cannot forget about it. But if you want to understand the behavior of your system, use profilers to capture information how your system behaves. So yeah, the performance test, the one of output of our performance test is the profiler recordings. So whenever you in our team go to the profiler to the benchmark results, you see the number, latency or throughput, and you have a link to profiler recordings to understand what happened. Which leads us to anti-pattern number two. Uh, I know this will be kind of depressing presentation because I said use profilers, and on the second slide I say profilers are lying. It's you need to be aware of the limitations, and I think the great thing you can do is to watch Nitsan Rakat presentation. Profilers are lying hobbies. But I can summarize it for you because it's like hour-long presentation. So basically, in a world of profilers, you have two possible ways to record the profiling data. One thing is sampling profilers, and the other thing are instrumenting profilers. For sampling profilers, as the name say, you have a sampling rate. So every 10 millisecond, 100 millisecond, the system stops for a minute, captures the behavior of the application, like current live threads and thread stacks, records this information, and lets the application go. The problem is if your method is faster than the sampling rate, then you may miss some important details. Okay, because the method will not always show on the recording. So you can of course say, okay, I need real information, so I will use instrumenting profiler because sampling profiler can hide some tricky parts of your code. Like for example, you have super fast method that is faster than sampling rate, and you call it in a loop, which is like super long hot loop over big array. So you will not see all of the samples and all the cases when you call this method. So you say, okay, let's use instrumenting profiler. The problem with instrumenting profiler is that it modifies your code. So actually, when you run performance tests with instrumented code, you run code that is different from the code that is in production. Things can go wrong. So it will show you really like precise information on what your application was doing, but is doing, but the numbers you get, you can just throw it to trash. Basically. And it's even more interesting if you are running like profiling applications written in managed runtime languages like Java, C Sharp, Python, JavaScript, where you have different aspects of the runtime like garbage collection, safe pointing, just-in-time compiler. So your managed runtime will do some extra thing, and the behavior of the instrumented code can impact the behavior of garbage collectors, can impact the behavior of the safe pointing or just-in-time compilers. So yeah, the application will behave differently. So that's the problem with the profilers. Of course, I try to bring hope after every pattern, so there will be like solution slide. First is you have to be critical with the profiler results. If you don't see something on the profiler recording, it doesn't mean it didn't happen, okay? Because you use instrumenting profiler. I mean sampling profiler, I'm sorry. And before you start profiler, think about it, what you are looking for and what you are expecting to see, like specific stack traces. Because if you don't see it, it means somebody is lying. Of course, it can happen that you run wrong configuration, but if you don't see what you expected to see, it doesn't mean it didn't happen. I use this quite often with my team. It's like with profilers, it's like with doctors, never trust a single profiler. So try to run second one. Yeah, but it's different. It uses different techniques, or does the instrumentation different, or does sampling in a different way, or uses different methods for sampling, and compare the profiler runs from two different profilers. And what I think is in my case, most helpful is when I look at the profilers and at the same time, I look at the metrics and performance counters. So I look, for example, how many times the endpoint was called, or I look how much memory was allocated at the time of running benchmark, or check if the database was invoked and how many connections were created. At the same time, to confirm that the monitoring and counters will say, okay, things happen for sure, and if you don't see it in profiler recording, means the profiler recording is incomplete. So use two sources, like either second profiler or use performance counters or metrics to confirm the findings from profiler. Another thing you can do is design factorial experiments. So whenever you design a performance test, think about the parameters of the test, like dataset size, number of concurrent users, and try to run different configurations of the same benchmark. I love baseline tests. So whenever we start with the new benchmark, we are trying to look for the baseline. Like for example, okay, what is the performance of the system with empty database? Okay, this is our baseline. Uh, it's always good to ask another human being and ask for a review of your performance test from somebody else. And yeah, that's thing. And of course, oh, I forgot about it. Make sure that the benchmarking environment is safe. It means there are no interruptions from other processes. You are not running performance tests in production or something like this. So yeah, these are the things you need to take into consideration. Let's move to the next anti-pattern. And I think yeah, that can be interesting because you do performance testing for a reason. You have a question and you are looking for some answer at the end. The thing is, are you asking the right question? What I mean by this is like the performance tests have layers, and there are different kinds of performance tests, and every kind of performance test needs another design of the data set. It needs another design of traffic shaping. So the first thing is what you are looking for from the performance test, because I can see there are like different types. Yeah, you have latency test where you are looking for the end-to-end transaction time. You have throughput test where you are looking basically how many concurrent transactions you can handle at specific time, and then you have load test when you say, okay, I expect 10,000 users, concurrent users. Will the system handle this? So you are not looking for maximum throughput. You are looking for a situation when, okay, you know how many users you will get. Will the system survive? So that's the difference, and you need to design this test in a different way. Then you have stress test, where you basically try to kill the system. Yeah, you put so much load on the system and see when the system breaks. You start seeing like 500 HTTP codes from your system, or it doesn't respond at all, and so on. Then you have endurance test, which are kind of like a stress test, but for a longer period of time. So you don't want to break the system. You want to keep it at like 90% of capacity, constantly hitting with the traffic, and do it for like days sometimes to understand if you have maybe some kind of nasty memory leaks, which are really small but accumulate over time, or you have connection pull leaks and things like this that only will show during extended periods of the test run. Then you have capacity planning. Then you want to see how well the system scales. So basically, you are trying to run with 20, 40, 80, and more users, and see what's the latency of the system or throughput of the system with growing number of users. So you want to understand your scaling capabilities in the system. And of course, something I never did, but I mentioned it, is degradation test, is the performance test when one of the component of the system fails. Like, in a microservices world is the question, what happens when the downstream microservice fails, you have circuit breaker, and how well it will respond with the system, but its downstream will not respond. But to be honest, I never was in a situation to had to test it. So you need to pick one, and you need to like ask yourself a question. Okay, what do I want to know? Do I want to know if the system is scalable? Do I want to know the breaking point of the system, or I'm just interested in latency? There is one special type of layer of performance tests. Sometimes they are not even included as performance tests. Is microbenchmarks. So for me, microbenchmarks are like unit test of the performance of what, because when you think about performance tests, you think about like end-to-end testing. You start the whole system, you have your database running, you have a microservices, I'm sorry, uh, everything looks kind of like production, and you are testing the system as a whole. Micro benchmarks are different because you don't test the system, live system, but you test specific function. Like in our case, for example, we are testing how much time it takes to add and return an index to a database, or how much time it takes to retrieve property from our graph. So this is really fine-grained small tests, which are pretty good at like when you try to optimize your code. Because you don't have to run the whole machinery, you can run it on your laptop and try to optimize your code, gathering the profiler recordings as you run. Of course, the infrastructure is easier to maintain because you run single functions like unit tests. It is still hard to get right because you need to understand the runtime and hardware, but they are pretty good at small optimizations and finding bottlenecks in your code and fixing stuff in isolated setup. Okay, we are like halfway done. I'm just checking the clock, and it looks pretty good. So let's move to the next anti-pattern. If you have questions, oh, I forgot about it. If you have questions, please ask. I will respond at the end to your questions. So don't afraid to write comments. Yeah, the fourth quite interesting thing is latency is not throughput. You would be amazed in like conference discussions on corridors how many people use latency and throughput interchangeably. It's like in the same sentence they use throughput and latency, and they think it's the same, which is really annoying. So the problem is that the latency is a function of system utilization. Yeah, the more your system is utilized, the higher latency is. So it doesn't. This is not simple, relation between the latency and throughput, because it all depends on the system utilization. And system utilization, it depends on how many concurrent users you have and how long are your method calls. Yeah? So basically, as you can see, with the utilization, the response time grows. So you cannot do a simple math to say, yeah, you see that thing. Yeah, I just look at the comment. Sorry. So you cannot exchange and you cannot use these things. So I think I don't see this a lot, but I would expect when somebody says, okay, at 99 percentile, I have 100 millisecond response time. There always should be a follow-up information. What was your query per second at this time? Yeah, was it like 100 millisecond response time for 100 queries a second, or was it 100 for 1,000 queries a second? Because this information which should always come together, in my opinion, because it will tell you how much, at least will give you impression how much the system was utilized during the testing. And then we move pretty fast to the anti-pattern number 5, which is how to mirror your production system during your performance test. because it's like famous DevOps quote. It works on my computer, and for performance, it's performance testing is always it was fast on my computer. It was fast in testing environment. Everybody's happy. So I think for me, after all these years, it is still a complex topic, and I still try to find time to like read more about it and get better at it. Is modeling the workload. This is how I feel when I do the workload modeling, basically Monty Python. So when you model your workload and you model your performance test, there are like a lot of things. I put few things here in like writing. I don't think it's all, but you need to take into consideration that you have different actors in the system. So, for example, if you have an e-commerce site, you have people that are just searching, yeah, and it's probably mostly 99% of your users that are just browsing and looking for something to buy. Then you have a group of people who are doing transactions and buying something in the system. Then you have on the other side people who are suppliers of goods to your e-commerce platform, and they put the information about stocks from warehouses and so on and so on. Then you have like administrators, integrations, and so on. So you need to think about different actors in the system that can be the system at the same time. Then, of course, the data sets. So how big is your data set? How big are your tables? How big is your product catalog? How many users you want to simulate? Uh, things like data traffic shaping. Is your system under constant load, or is it like 8 to 5 and then nothing? Or maybe the system is hit only during the weekends. The thing is that if you have like variation in traffic, the system can be different. Like, Java will need to warm up, for example, because it's JIT compiled. So whenever you don't have traffic, it will decompile the method, and then when the traffic hits, it will have to optimize the method, compile the method again. So traffic shaping is pretty important. Type of operations. Do you have only create, or you have mixture of create, delete? So what kind of things people are doing in your system? Are they creating new entities? Or are they deleting? Operation dependency, which is, I think, mm, pretty complex, is okay. When somebody searches, after the search, he will probably go and log in. And after login, he'll probably go and add something to the shopping cart. I'm using the e-commerce example because I spent a lot of time in the e-commerce site. So you need to think about dependency and like the user journey for the system when you are designing the um, performance test. Another thing is operations are interleaving. Somebody is doing, buying the stuff, and you run out of stock, so you have like concurrent access to item, uh, and then you will need to think about concurrency of these operations. Of course, time is important because usually what happens is your databases grow, uh, and as your databases grow, it changes. The databases changes characteristic. Yeah, so you need to reflect sometimes that actually you have bigger and bigger data set, and of course data latency, like things that remove stuff from database and so on. And these are just things I came up to my mind like late in the evening, like, okay, what you need to think about when you design the workload. uh, and then we go into territory of data sets, where when you design your data set, your database for testing, you need to think about first cardinality. Yeah, the database is what I learned about databases being in NEO, is like cardinality is king. If you understand cardinality, if you can predict cardinality, then your database will be great. But you need to think about use cases like, okay, I have customers who have one item in a shopping cart, but I will also have customers who have 20 items in the cart. That's different cardinality. Yeah, it's different, probably maybe different query plan. Uh, You need to think about indexes. Yeah, make sure that you have the same indexes during performance testing. And of course, what is your live data set? So, your database may have 200 terabytes, whatever, you know, a lot of terabytes, but only the part of this data is actually used. In most databases, my impression is like the most of the data could be archived. Yeah, this is like cold data. And there is this live data set that needs to be in memory to really provide good performance. So you need to think when you design what is your live data set actually, not the total size of your database. Because it's in our system at the end there is some database. At some point of time, clicking for your deployment diagram, you will find that you will have database. So that's why the design of the database, the data sets is so important to perform good quality performance tests. So what you need to look out is think like cardinality to make sure that when you run performance tests, you don't have queries that sometimes return one and the same query for other user returns 200, because then your response times will be different and you will have a lot of uh, noise in the system from the super quick queries, and probably you will be able to execute more short queries than large queries. So when you design your data set, you need to find the parameters to make sure that you return the same amount of rows during the performance test. And of course, how much of the data set fits into memory. Uh, and you need to keep an eye on the variance. Okay, so basically make sure that you don't have the results and the response time from your performance tests all over the place, like from 10 milliseconds to 1 second, because then come the statistics and average, and it won't tell you if your system is performing good or not because you have different uh, sizes of the data sets. Okay. So watch out for the number of page cache evictions, size of the page cache, and of course slow queries and query plans. So this is things that it's worth to monitor during doing the performance tests. One thing that we are doing in the team, it's pretty helpful, is we are monitoring the size of the results returned from database, and we put it on charts showing, okay, during the execution of the benchmark, this was the uh, no, this is the number of rows you get during the execution of the benchmark. So that's the one thing. The second thing is coefficient of variation. This is a thing from statistics, and this is kind of ratio showing you how much you have deviated from the mean. Yeah? So if you have high standard deviation, it means your test is unstable. Unstable in terms of returning results. And of course, on top of it is modeling test environment. So when you have your data and you designed your proper traffic and you did everything around, kind of operations and operations interleaving in your performance test, you need to think about, okay, what kind of instances you will use. You will use the same instances as in production, or maybe different. Make sure that the network is isolated from production, that the infrastructure is isolated, so you are not running your bench performance test on the same server that runs production database. Things can happen. Make sure that you have the proper configuration of components, and they don't deviate too much from the production settings. And something I don't have good answer for, to be honest. It's all like every time I do it, it's like, okay, we'll hack something. It's the third-party integration box, because during the performance test, you don't want to like exercise your payment gateway. Yeah, you don't want to test performance of your payment gateway or whatever third-party integration you have, and probably you have a limited number of queries and so on and so on. So usually, what I recommend, I'm not super convinced to it, but I think the only thing that works is having mocks for during performance test for the third-party integrations, and mocks responding with the same constant time. So to remove this thing from your calculations. Yeah? And yeah, you have to remember it will always get worse in production. Yeah, it will. And yeah, we are getting here to the sixth anti-pattern, which is quite complex. Is remember I said profilers are lying. Actually, the load generators are lying as well. So what I'm thinking when I say load generators are the tools that simulate traffic. So JMeter, Gatling, K6S, uh, there is Locus from Python. There's a lot of things that you can use to simulate traffic. And for a long time, all these things were lying to you. The problem is now fixed in most of the load generators, open source or commercial, but you need to be aware if you pick something that, we are testing something that is not HTTP performance testing, or you need to make sure that your load generator is not lying. And what is the source of this lie? So there's some kind of odd behavior called coordinated omission, and it was described by Giltene, CTO of Azure, that your system under test can impact the behavior of your load generator. So basically, in a simple word, saying the more you put uh, pressure on your system, the more traffic you generate from your load generator. If the load generator is written in a wrong way, designed in a wrong way, the slowing down of your system under test will slow down the load generator, and it will not generate the expected request per second. So there is some kind of a feedback loop between the load test generator and the system under test. And yeah, the system under test being slower causes this load generator to not generate enough traffic. Pretty good blog post describing and explaining how the coordinated omission works and why it happens. And basically why it happens is, in a world of performance, there's this discussion about open model versus closed model system. And in the closed model system, I should change the order of these things. In closed model systems, the new job is sent to the system only if the previous job is finished. So in closed model is you send request, you wait until this request finishes, then you execute the next request to the system. That's the closed model. And open model systems is a situation when the requests to the system arrive independent of each other. So they don't, coordinate. And as you can, your intuition will say, it's open model systems are close to reality. It's like our system we have in production are open model systems. You don't control when the request will come. Okay, in a context of a single user, yes, but in a context of all requests in the system, no. And closed word you can describe as this lovely performance test here, for loop, when you make HTTP request and wait until it completes to execute a new one. And then you have, like in open world, you just keep sending requests. You don't wait. Of course, you cannot create new thread every time. Probably, if you are in newest Java and you have Project Loom, you can try to do it like this. But this is the problem, but you cannot create infinite number of threads to design the open world kind of open world load generator. Because what you do usually is, this is the essence This is like pseudocode for every load generator. You have a loop, you record the time when you start, you make a request, you record the time when it's ending, you measure the latency, record somewhere, and it's the whole magic. But you cannot have endless number of threads to model open system. So what you can do, you can have two approaches. One is static schedule and the other is dynamic schedule. Is in static schedule is okay, you try as hard as you can to run your request at expected times. Okay, so your scheduler of requests will try to keep up to your schedule. Like, okay, send request every 10 seconds, 10 milliseconds. It will try to do it with the limited number of threads that it has, but it will try to squeeze it in. And dynamic schedule is where you execute next query with some delay between first and second request, but not shorter than this delay. Okay, so this is like kind of theoretical ways you can solve it. And technically, you can solve it in two ways. One is queued approach. So basically, you have thread pool. Yeah? You have thread pool. You have queue of requests, and you try as fast as you can to execute your queries. You just asynchronously put something on the queue, next request, and most of the load balancer work this way. Yeah, but there is a queue, there's limited number of threads, and they try to execute the request as fast as they can. Okay. And then you have queueless approach when you don't have a queue, but basically, if it's time to execute next request and you don't have a thread to do it, you just skip this request. Okay, so you don't wait in the queue. You say, okay, I want to send next query. There's no available threads to do it for me. I skip it. Okay. Another thing you can do is latency correction. So basically, you measure the difference between when you actually executed the query and the time when you're supposed to execute. Okay. And then you do correction based on this calculation. But you said, okay, I should execute it 10 seconds ago or 10 seconds ago, but I execute it now. This is the difference between the expected time to be executed and actual time. And I use it to correct the latency response. Okay. The thing is that in most cases, you shouldn't worry about it at all. But if you select some new tool, just make sure that they support and solve the problem of coordinated omission. Another problem is time. So basically, measuring time takes time. That's the one thing. It's like it's not cheap. You don't get the time instantly. You just ask for time, and when you get the time back, it's usually not the time. It was sometime in the past. Then you have a granularity, so the minimum difference between the two calls to your clock. Okay, and in most systems you don't have like 1 nanosecond granularity. It's something worse. Yeah, and it's getting worse in multi-threaded systems because clock taking time doesn't scale well in multi-threaded systems. If you want to know more, and we don't have time to all of this, of course, I recommend you to read Nanotrusting the Nanotime by Alexei Shipilev, where he does like really deep dive why taking time takes time. And as you can see, it takes around 30 nanoseconds. And also the granularity is around 30 nanoseconds. On most systems, it depends on the operating system and CPU, but yeah, you have 30 nanoseconds difference. Okay, and the last thing, we are getting closer to the end. It's actually the last slide. Is if you are looking at the performance test, of course, we look at throughput and latency, but we tend to ignore system utilization, so how busy the system was during time, the saturation of the queues, you know, request waiting for the processing, and of course the number of error responses. And I show you like a real story. Ages ago, I was during the deployment of one of the SaaS platforms I was working with, and somebody during the release came to me and said, "Oh man, this is so great! We are 20 something percent faster than the previous release." In the performance world, when you see that something is 20% faster, you get to be suspicious. You know, usually you win like 5% and you are then lucky and, you know, nudge yourself in the shoulder that you did a great job, but 20% is suspicious. What we found out is the development team changed the URL address of one of the endpoints, and we didn't know about it. So our system was testing 404 response code performance. So how fast we were getting the not found from HTTP. And because we are not monitoring the amount of errors during tests, we didn't know whether actually we are hitting the wrong endpoint. And at the end, you know, people thought that this release is a great success, and it wasn't because we were just not monitoring the error responses. So make sure that when you run performance tests, you monitor not only throughput and latency, but also system utilization, saturation, and errors, because they can give you a great insight. And the final boss. In my opinion, but I am biased. I'm doing, you know, performance for the last couple of years, and I'm like in love with it. I love it. It's really cool. But I think not having the performance test for it's one big anti-pattern because you know. When you realize you need it, it will take you ages to build things. And usually you build what I saw in many companies I help with is like people think about performance after first disaster in production. Yeah. Until then, everything is fine. People ignore it. But when it hits and your system goes down for a couple of hours, in my record was 40 something hours, system was unavailable for users because of the performance problems. It's really too late. And as you can saw in this presentation, there is a lot of things you need to do to build proper performance test suite. So don't wait until disaster comes. That's the last slide. Thank you very much.
All right, thank you, Eric. It was very interesting presentation, as we have as well those comments on our channel. It was interesting as well. And you told in the one of the last examples some story from your life that it was about short link which was replaced, and the performance went up 20%. And do you have maybe any more like examples of, or maybe like challenges or most common mistakes which are made during the performance testing?
Mm. Oh, you know, it's. I think that the greatest example I have is like what we did last year when we were testing our database uh, on different platform. It was basically not Intel but ARM CPUs. And when we got back the results of the performance test, it was like not the thing we were expecting to. And we spent a lot of time because we had some assumptions. I think this is the really dangerous thing when you do performance testing is your hidden assumptions in your brain. But you think you know how things work and you don't check it and you continue your investigation with the false assumptions. So we were assuming something about how JVM on ARM works, and we were pretty confident that we are right. The system is wrong. And then we found out that actually we didn't know that ARM, and especially Java on ARM, does few things differently. And it's not because our code is wrong, but this is like inherent part of the system. It's normal behavior. So yeah, one of things that hits you the most is your silent assumptions. Another example is like somebody says, "Okay, this is fast. This has to be fast." If you hear it from somebody that has to be fast, it means he probably doesn't understand what's going on. It's pretty often with development teams like, "Oh, it has to be fast because there are indexes. When you go to the database and you see there are no indexes to the database because somebody assumed that somebody will create indexes." So I think this is like really common pattern. This hidden assumptions, how things work or how things are configured. You are chasing the problem that actually doesn't exist, and you waste a lot of time. So yeah.
And as you said, a lot of things are lying to you, as it was mentioned on the presentation. So it's
Yeah,
sometimes.
I need regular visit to psychologist. It's like
All
you
right, but
open, this is how your works look like. You come in the morning to your work, you open the measurements from the night because we are running the performance tests usually overnight. You open it, it's like, okay, who's lying now? It's like you have a couple of charts and just select which one is lying.
but you said you love it, so
Yeah, it's addictive. I'm addicted to looking at charts. It's like lines, and it's lovely.
all right, I'm happy to hear that. So thank you, Jarek, for your time. We were really happy to have you today and listen
Thank
to
you.
your presentation. It will be, of course, on our YouTube channel, so anyone who was not able to watch it today live, you may find it in there. And well, we see you during the next time. Thank you. Bye
Thank
bye.
you.